Hello, everyone. I am honored to have the chance to share our work here at IEEE Census 2025. My name is Shichao. I come from Tianjin University. My presentation is a high precision and large range iontronic flexible 3D force sensor for robotic interactions. And I will report this work from 5 parts. Robots and their application domains have attracted widespread attention, while robotics has a long-established history in industrial settings. Evolving societal demands have recently spurred growing interest in new applications such as medical surgery, home and personal services, advanced manufacturing, and entertainment. To enable these capabilities, robots require a suite of sensors to perceive changes in their external environment. Among these, tactile sensing represents a crucial component of active perception. We believe that tactile information, particularly three-dimensional force sensing, or 3D force sensing, forms a fundamental basis for achieving. Hello, everyone. I am honored to have the chance to share our work here at IEEE Census 2025. My name is Shichao. I come from Tianjin University. My presentation is a high precision and large range iontronic flexible 3D force sensor for robotic interactions. And I will report this work from 5 parts. Robots and their application domains have attracted widespread attention, while robotics has a long-established history in industrial settings. Evolving societal demands have recently spurred growing interest in new applications such as medical surgery, home and personal services, advanced manufacturing, and entertainment. To enable these capabilities, robots require a suite of sensors to perceive changes in their external environment. Among these, tactile sensing represents a crucial component of active perception. We believe that tactile information, particularly three-dimensional force sensing, or 3D force sensing, forms a fundamental basis for achieving key robotic capabilities, such as fine assembly operations, safe human-robot collaboration, excellent environmental adaptability, and object detection and recognition. Currently, numerous studies have reported the three-dimensional force tactile sensors based on various sensing mechanisms, such as piezoresistive, capacitive, piezoelectric, and triboelectric approaches. Among these, iontronic sensing has emerged as a promising new mechanism with significant potential. By surface engineering of ionic materials, iontronic sensors can achieve high sensitivity over a wide detection range, often hundreds to thousands of times higher than conventional non-iontronic devices, while also exhibiting immunity to electromagnetic interference. Our iontronic flexible 3D force sensor consists of 4 parts: a structured PDMS layer, top and bottom electrode layers, an energy layer, and sandwiched between them. The structured PDMS features a flat plane with 3x3 array of bumps on its surface, serving as 3D force transmission structures. These bumps are capable of deforming and twisting under tangential forces, leading to traction and compression on the plane, converting tangential force into differentiated normal force to the sensing area. The ionogel layer was fabricated by curing the polyvinyl alcohol and phosphoric acid solution on a sandpaper template, resulting in a hierarchical microstructure with interlocking features. Both the top and bottom electrode layers contain a 6 by 6 square nanosilver electrode array, with one array connected in rows and the other in columns. The vertically aligned square electrodes sandwiching the ionogel form an Iontronic cell. Each 3D force sensing unit comprises a 2 by 2 Iontronic cell array topped with a bump. And first, we characterized the performance of the microstructure of the ionogel to evaluate its suitability for tactile sensor applications. The ionogel exhibits high sensitivity across a wide pressure range of 0 to 500 kilopascal, with a maximum value reaching 4.1 per pascal. It also demonstrates excellent pressure resolution, a skin-like detection limit as low as 21 pascal, and fast response and recovery times of 39 milliseconds and 41 milliseconds respectively. The microstructure fabricated using a sandpaper template significantly enhances the compressibility of the sensing ionogel, thereby expanding the variation range of the iontronic response. This structural design enables a pronounced change in sensor output under increasing pressure, which contributes to high sensitivity and excellent pressure resolution observed. Next, we conducted a series of COMSOL simulations to optimize the structured PDMS layer design. The results demonstrate that the layer transmits applied normal and tangential forces to the underlying iontronic cells through distinct modes, enabling 3D force sensing. And next, we built a mechanical test platform and evaluated the output characteristics of a single sensing unit in the flexible 3D force sensor. A plastic bar with the same surface area as the bump was fixed on a stationary stage, while a commercial force torque sensor was mounted on a 3-axis displacement stage. The bottom of the tested 3D force sensor unit was attached to the surface of the commercial sensor to ensure that when adjusting the 3-axis displacement stage, the force applied to the commercial sensor was equal to that acting on the single sensor unit. When normal force Fz is applied, the bump is compressed, resulting in a uniform pressure distribution across the 4 iontronic cells. Within the normal force range of 0 to 20 newton, the 4 iontronic cells of a single 3D force sensing unit exhibit highly consistent responses. When tangential force Fx or Fy is applied, the responses of the iontronic cells at the near and far ends show clearly distinguishable trends. The inclination and deformation of the bump cause compressive stress on the 2 iontronic units at the far end of the force direction, while tensile stress exerted on the 2 cells at the near end, leading to differentiated responses. And due to the silicon rubber bonding between the plastic bar and the bump, the tangential force range was extended to -8 to +8 under conditions with negligible normal force. And subsequently, to address the challenge of insufficient samples when applying machine learning methods to decouple 3D force, we developed a custom data acquisition system based on the commercial software National Instrument LabVIEW. This system enables synchronous acquisition of signals from both commercial force sensor and our sensor circuit, thereby achieving continuous calibration of the flexible 3D force sensor. And by adjusting the 3-axis displacement stage to apply 3D force to a single 3D force sensing unit, the coordinates of the 3-axis displacement stage and the output of the commercial force torque sensor and the response of the flexible 3D force sensor was matched one by one. And finally, a continuous 3D force dataset containing more than 240,000 samples was collected in real time across the normal force range of 0 to 15 Newton and the tangential force range of -8 to +8 Newton. The data distribution is shown here. And we then employ the mean absolute error and its standard deviation as evaluation metrics to assess the 3D force decoupling performance of 4 commonly used machine learning algorithms: back propagation, support vector machine, random forest, and XGBoost. A tenfold cross-validation was conducted on the dataset, with results presented here. The large and densely sampled dataset enabled the random forest algorithm to achieve exceptionally low 3D force decoupling errors across the entire detection range. And also, due to its minimal requirement for hyperparameter tuning, the random forest model demonstrates unique advantages in handling large-scale 3D force decoupling tasks. Here presents a comparison between selected true and predicted values from the tenfold cross-validation using the random forest model. The results indicate consistently low prediction errors on both training and testing samples, highlighting the model's robustness and generalization capability. To validate the sensor's capability for real-time 3D force sensing after dynamic calibration, we designed an experimental scenario involving continuous application of 3D forces. The flexible 3D force sensor was fixed on a flat surface, while the commercial force torque sensor equipped with a plastic bar at its bottom was mounted on a programmable linear motor capable of moving at a constant speed. As the motor drove the commercial force torque sensor and the plastic bar into interaction with the flexible 3D force sensor, the LabVIEW software continuously acquired the sensor's output signals and loaded a pre-trained random forest model to perform 3D force decoupling in real time. When the plastic bars slide sequentially across the 3 sensing units in the second row of the 3D force sensor, the corresponding channels successively decouple the 3D forces detected by each individual sensing unit. The decoupled outputs showed high similarity to the readings from the commercial force sensor, just as shown in the figure, demonstrating that our sensor possesses excellent capabilities for real-time 3D force sensing. In summary, this work presents an Iontronic flexible 3D force sensor with a normal force detection range of 0 to 15 Newton and a tangential force range from -8 to +8 Newton, and a data acquisition system for tactile datasets collection, enabling time-efficient dataset building and easy to use for machine learning methods, and a real-time 3D force sensing scenario to show its potential in different application areas. And finally, I would like to share our future research directions and plans. As our sensor offers high precision, wide range 3D force tactile sensing, and moreover, thanks to its convenient data acquisition system, the tactile datasets can be efficiently constructed. And moving forward, we will focus on 2 key aspects. First, We would like to further improve our sensors resolution, mechanical stability, and environmental adaptability. And based on this, we will integrate it into robotic hands and investigate the cooperative mechanisms among various grasping postures, 3D force information, and feedback control, with the goal of advancing applications in adaptive grasping and object surface recognition. This work was directed by Professor Li Dachao and Professor Zhang. And this is the link of our lab. So if you are interested in our research, please feel free to visit our website. Or if you have any wish to collaborate with us, please feel free to contact us. And also, this work is supported by state-key laboratory of precision measurement technology and instruments. And here are some views of Kenyan University, and that's all. Thank you, guys. Thank you for all your time.